Hi everyone, welcome back. What we're going to do is in this video, we're going to discuss reversibility in acid-base reactions. And the reason why this is important is, and I'm just going to do it pretty quick using like a couple of examples, okay? The reason why this is important is because what we know based on the introduction to acids and bases is that when you have an acid, it reacts with a base to give you a conjugate acid and a conjugate base. That means you have an acid and a base on your reactant side, and you have an acid and a base on your product side as well. And if you forget about this, forget or just ignore the conjugate part of it, these species are still acids and bases. So what that means is, in principle, those two could react with each other and take you back to your reactants. Okay, that is a possible. And this is possible, and it happens in most all uh, almost all acid-base reactions, except for a few cases where maybe there are other factors involved and they basically make the reaction irreversible, okay? But in most cases, acid-base reactions have reversibility to some extent. Now, some could be, some could be more favorable in the backward direction. So we'll talk about all of these aspects in subsequent videos, but let's look at a few examples quick to understand what we're talking about here. So let's consider simple example, HCl plus sodium hydroxide or something, or maybe let me use another acid. Actually, we've been using HCl. So let's say we have HBr and we have sodium hydroxide, Na plus and OH minus. So acid, base, the base abstracts the proton, electrons move towards the bromine. This would give us water. Now I'm going to write out the water molecule. The hydroxide, when it accepts the proton, would give us water molecule, plus it's going to give us Na plus and Br minus. Okay, the water is going to be our conjugate acid, sodium bromide, or the bromide specifically would be our conjugate base. Now, one thing I want to point out is there is no specific order in which these species have to be written. So you could write the base first and the acid later. You could write the conjugate base first and the conjugate acid later. There's no rule that they have to be written or they must show up in a specific sequence. Okay, so please don't keep that. I think I've been writing them all like uh, uh, pretty consistently in a certain way, but there is no rule like this. Okay, so we made our conjugate acid and conjugate base. So what I'm saying is essentially on our product side now, the conjugate base could go and accept a proton from the conjugate acid because this is an acid, that is a base. And when that happens, this electron pair here from the bond, okay, the shared pair of electrons would be pushed to the oxygen atom. And if you look at it, what we're doing is we're making a bond between the bromine and the hydrogen, which will give us HBr. And we're pushing the electrons away to that oxygen that would give us hydroxide. And so now the sodium would be here. So the reaction is reversible. Now, for now, I've drawn equal arrows in both directions. But like I said earlier, to what extent this reaction is reversible, or to put it in a different sense, is the reaction favored in the forward direction or the reaction is favored in the backward direction? That is some more assessment that we have to do, and we will talk about that. Okay, so that would be one example. So the reaction could go forward or backward. Okay, Let's pick up another example here, making it a little bit more of an organic acid here. Okay, so let's say we have this, which is acetic acid. This is acetic acid uh, or vinegar. That's what this is. So let's say if we have acetic acid and we have sodium methoxide. Okay, so I'm drawing a bit more involved and complex organic acids this time. So acetic acid reacting with sodium methoxide. Again, as I mentioned earlier, we have oxygens on this side or in this species, but its name suggests an acid. But let's say if you don't know the name, okay, oxygens on this species with lone pairs. We also have a hydrogen that's connected to an oxygen atom, which means this hydrogen is going to be partially positive. And on the other hand, we have the oxygen with a negative charge. So like I said, whenever you see this combination, uh, uh, I think in a lot of cases, potentially the species with the negative charge is going to be our base. So what we're going to do is we're going to take the negative or the electrons from this oxygen and grab the proton. Okay, so the base accepts proton. These electrons go to that oxygen atom. And so the resulting species, if I draw it, if I draw this species, what's left would be CH3, C double bond O with an oxygen, 3 lone pairs. So that would be a negative charge. And on the base side, we have CH3O, and the oxygen used one of its lone pairs to abstract this hydrogen. So what we would get is CH3, O, and then H. The oxygen has 2 lone pairs on it. Okay, so now if you look at it, this was our base. We used this as a base. So that means base, when it accepts the proton, would give us the conjugate acid. That must be our conjugate acid. And the acid, when it loses its proton, we get the conjugate base. Now, there is sodium ions here, was balancing the charge of that oxygen. Now, this oxygen has a negative charge. So the sodium ion is actually with this oxygen. So we can put the sodium over there. So we've completed an acid-base reaction there. But again, we have a base and we have an acid. So in principle, the base can abstract the proton from the acid, and electrons from here move to that oxygen, and that would bring us back. Okay, but as I mentioned earlier, is the reaction, acid-base reaction, favored in the forward direction, or is it favored in the backward direction? That is something that we're going to learn next. Okay, how do we assess that? Another thing, the acid and the base are defined by how they are written. If I were to flip over this equation so that sodium bromide is here and then water is here, then I would be calling those my acid and base. So again, it is defined by what is written on your reactant side to some extent, okay? Just as a convention, that's how it's defined. So don't think that if you look at this reaction in the reverse, then you would still call whatever is on the other side as the acid. But it really doesn't matter because it is the same thing happening on both reactions. Okay, so that is the reversibility in acid-base reactions. And like I said, what we're going to do next is learn how to determine which of these reactions is more favored. Does the reaction go more in the forward direction, or is it going in the backward direction? Forward is favored or backward is favored? That is what we're going to do next.